Good morning.
Morning.
Okay, not bad. Okay. Okay, I wanted to start with the homework. I gave you this assignment to think about. I didn't mention it. I hope you recognize the window in Notre Dame Cathedral in Paris there. So the question was, do cathedral glasses flow appreciably in 500 years? And I'm going to just briefly say how I did the problem. I had given you this graph. I gave you enough information to figure out what the activation energy is for that, that glass, sort of the out of equilibrium tau alpha behavior. This is a hard number to measure. Ludovic and I were just talking about this. But I think this is a reasonable approximation. For many systems, it works out to be about 32 kTg. So you just need to extrapolate way, way, way the heck down in temperature, because you have to get all the way down to 300 Kelvin. And if you do that, you estimate not the equilibrium structural relaxation time, but the initial structural relaxation time of the just quenched material at 10 to the 23 seconds. Okay, really big number. Okay, so it's not going to flow. If you're interested in a more detailed calculation, I refer you to this reference, which considers it's basically the same calculation. Okay. So let me introduce the topic of this third lecture by using this very colorful image of the potential energy landscape, which I borrowed from De Benedetti and Stillinger, and then I've made some additional marks on it. You all know the idea of the potential energy landscape. There are basins where particles may be, this whole system, this is a 10 to the 23rd dimensional object. The entire system may be transiently trapped. There are transition states between those barriers that have to be crossed for the system to structurally evolve. For a system at equilibrium, at high temperature, our potential energy is high, and so we're experiencing what's going on sort of at the top of the landscape. So Tc here would indicate something like the mode coupling temperature, Tc. As we cool a supercooled liquid, it stays in equilibrium for a while. The typical Tg that we would get to at cooling, say, 10 degrees a minute, we would get down to something like this point here. So now we're exploring the behavior of the basins that are found lower in the energy landscape. There are fewer of them, right? This is related to the configurational entropy going down. And then if we're making a liquid-cooled glass, we continue to cool, but to a first approximation, we get stuck because we're out of equilibrium. Okay, so we're stuck at this position on the potential energy landscape. Now, if we're willing to sit not too far below Tg and age for maybe a month or 6 months or a year, okay, the system will work its way down the landscape. It'll make a little bit of progress. And so maybe it'll get this far. And so as we talked about, as we go down the landscape, the barriers get higher. And so that feature is not illustrated very dramatically in this image, but I think it's a feature of real systems. So the question I want to pose today is what's going on down here? So if we stay away from the crystal and we go to the bottom of the amorphous part of the potential energy landscape, what are these states like? And sort of the traditional thing to call this state right here is the ideal glass. It's the bottom of the amorphous part of the potential energy landscape. And let me just point out all the things that are interesting about states down there. This whole business about the configurational entropy going away has to do, with how the number of states is getting smaller as we go down to the ideal glass. And so somehow that information is encoded here. Whether relaxation times actually diverge or not is somehow encoded in the barriers that are down there at that part of the landscape. If there's an interesting growing length scale in this problem, Somehow that's encoded. It's going to be most dramatic as we get to the bottom of the landscape. It somehow has to do with these states down here. As a material scientist, I might be interested in, well, what are the properties of this ideal glass? Is it good for something? Could we do something with it? And I might suspect that the ultimate material properties for amorphous materials, at least along some coordinate, might be found for these materials. They would be sort of the most extreme version. They would be highest barriers, most stable, that sort of thing. Okay, so that's the setup for today's lecture, is thinking about what we can learn from experiments about what's going on down there. Okay, so I think you already can start to sense the problem. We spent a year preparing our sample and we already got to here. Okay, maybe if we would spend 1,000 years, we'd get to here. Okay, maybe 1,000,000 years would get us to here. Okay, so this does not seem like a practical way to proceed. All right, so maybe some of you have thought about this option. There are glasses in nature. Okay, they've been sitting around at roughly room temperature for, in some cases, millions, hundreds of, maybe 100 million years. Okay, maybe we could make use of these materials to learn about the states that are deep in the energy landscape. So these glasses are really cool. They each has their own story. I won't tell all the stories, but I do want to mention them briefly. So in the upper left is obsidian. It's a silicate glass. It's a volcanic glass, okay? And you can tell it has important uses, particularly for Aboriginal societies. So that sample is amorphous. When it crystallizes, you see crystals in the material. It's really obvious when it crystallizes. And various kinds of dating has determined that you can have amorphous obsidian that's up to about 75 million years old. So that seems promising. It's been aging for a long time at room temperature. Okay. The next one over is a glass from the moon. Okay. So the Apollo astronauts brought back those samples. The scale is about, I think, 200 microns across for those little beads. So those materials have been glasses for, are you ready? 3.5 billion years. Okay. Turns out, for reasons I could explain, if you're a glass and you don't want to become a crystal, the moon is the perfect place. There's no humidity. Okay. There's lots of things that help. Okay, so this stuff here, since you've all seen Jurassic Park, you'll recognize that as amber. You have seen Jurassic Park. Yeah. Some, yeah, okay. Okay, amber is like resin from a tree, okay, that starts out sort of like sap, and then over time there's chemical reactions. Eventually it becomes a material that has a glass transition temperature about 100 Kelvin above room temperature, okay? And there are amber samples at least 200 million years old. Okay, so surely we can learn something important about the bottom of the potential energy landscape from these materials. Okay, so these materials, so I haven't told you what the TGs of these materials are, but these are high. This is maybe, I don't know, 1,000 Kelvin. This may be higher than that. Okay, so the big problem for these materials is that TG over T aging is too large. In fact, this is exactly the cathedral glass problem. These materials are so far below TG, the barriers, even in this relatively poorly formed liquid cool glass, you've cooled the material so far that it's not going anywhere. So essentially, aging doesn't happen. So if aging doesn't happen, then these materials aren't useful for getting to the bottom of the energy landscape, right? Amber, here Tg over T aging is something like, let's see, 1.3. And so this is close enough that a lot of aging can happen. And so there has been some nice recent work using ambers to try and understand what happens deep in the energy landscape. Greg McKenna's done this. Miguel Ramos has done this. And so far they've looked at like ambers from 10 different sources. And there's, unfortunately, I would say, a wide diversity in the properties of these materials. And so I think it's a little bit hard to infer from what's been measured what you would expect to see in a well-controlled experiment, where you actually know what the thermal history of your sample is, and you know that the sample has not chemically evolved during the aging time. Okay? So I hope you find that interesting. So naturally aged glasses are not going to answer this question. But I'm going to show you some materials that get us really close to telling us what is happening at the bottom of the landscape. But before we do this, it's time for class participation. So this is an in-class assignment, okay? So I've just told you how hard it's going to be to make an ideal glass. So let's suppose somebody did it, okay? And you're an experimentalist, and you have a lab, and they say, here it is. Here's the ideal glass. And you say, great, that's really exciting. Now, what experiment should you do to determine its properties? Okay? And I gave you a hint. You might want to think about, well, what are the special things about a stable glass, and can you somehow measure them? Okay, so I am ready to hear your answers.
Wouldn't age.
Wouldn't age, no aging. Okay. Or you do some test for aging. Good. That's what I'd expect.
The same enthalpy as the crystal in the same temperature?
Same enthalpy as the crystal. Let's say, let me slightly modify that and say it should have a really low enthalpy. I don't think there's any reason why it has to be as low as the crystal. Yeah. Huge kinetic stability.
Can you say that there's no aging in an ideal gas because the relaxation time will be exponentially large? So how can you say whether it's aged or not?
Well, okay, I think you've hit upon an important problem. It seems like the most obvious thing one of the obvious things you'd want to know about an ideal glass is, does it really have an infinite relaxation time, or how big is it? But unfortunately, you're expecting it's so big you can't measure it, right? So you'd like to measure tau alpha, but probably too large, which is disappointing because, of course, you'd like to know how big the barriers are down there, and this is the most obvious way to get there. Patrick.
I mean, we were discussing here. So if you did calorimetry and measured the free energy, once you've worked backwards, you should be able to work out that the configurational entropy is 0.
All right, configurational entropy. Now I'm going to pick on Patrick a little bit. Anybody see any flaw in that argument? Yes, I would say that's really the number one thing I would put on my list. I want to figure out what the configurational entropy is for this material, or at least the excess entropy. Yeah, let's settle for the excess entropy, okay? Okay, so
you can measure the entropy of your glass. If someone gives you the ideal glass, in principle you can cool it down to 0, but the entropy is 0, then you bring it back at the temperature and you integrate.
okay, so
I don't see any way of having this.
Yeah, okay. So let me just cut to the chase a little bit here and say, I think, so when I teach thermodynamics, I tell my students that in order to calculate an entropy, you need a reversible path. Okay, and this is the nub of the issue. Because if the relaxation times are getting extremely long, then I have to do my calorimetry at extremely slow rates to stay in equilibrium all the way along the way in order to have a reversible path. And so that's a problem. And if I have the ideal glass, what? Somebody gave it to me. Well, okay, yeah. So, all right, so this is perfect. You guys came up with the right list. And so, the story of my talk today, if you want to look at the outline for the 3 talks, the part in red is what I want to do today. I want to tell you about vapor-deposited glasses. And I want to show you that these materials are very near the bottom of the potential energy landscape. And I want to tell you about their properties. And I want to get at all of these issues that are on the board. And you'll see that I run into problems in trying to say something completely definitive about the relaxation time and the configurational entropy for exactly the reasons that we discussed. Yes?
Is getting a lower bound for configuration entropy useful?
It might be, sure. Yeah, I mean, yes?
If you had an ideal gas or ideal glass, would the low temperature behavior be very different because the 2-level system description?
Well, I hope so. That would be great. I'll talk about that too. Okay. Actually, I guess we didn't hit everything here. The other thing that you might say is, well, I know there are, in a liquid-cooled glass, I know there are relaxation processes that survive into the glass. Okay. We talked about these extremely low temperature processes. We also talked about the beta relaxation process. Okay. So I should look for those things. Okay, because those are things that are seen in glasses and don't require that I be able to get my material to undergo an alpha relaxation. Okay. All right, this is a good set of issues, and now let's see how much progress we can make. Okay, so let me give you the basic idea about what happens in physical vapor deposition. So we have a vacuum chamber. So this is happening in a vacuum chamber. We have molecules that are either sublimed or evaporated from a source. They fly through the vacuum ballistically. There's nothing to run into. They slam into a temperature-controlled substrate. Okay? Temperature of the substrate is really important. And if you've chosen wisely, they make a glass and not a crystal. Okay? In our experience, we almost always get glasses instead of crystals. But if you choose water, it's easy to get a crystal, for example. Okay, so we're going to make some sort of solid here. Let's say it's an amorphous solid. Why should it be interesting? So what is trying to be illustrated by this cartoon is the idea that molecules right at the surface move rapidly. Okay? They're not constrained in the same way as molecules are in the bulk. And that this motion that occurs on the surface is a kind of sampling of different ways of packing. Okay? Just like the sampling that would happen in any liquid as it's trying to get to equilibrium. Except here, if the surface is sufficiently fast, I could choose this temperature to be, say, 10% or 15% below the ordinary glass transition. Okay? So if I can succeed in using this surface mobility to equilibrate the material under those conditions, then it's going to be very low in the potential energy landscape. Okay? So I'm not going to show you this data, but there are experiments that directly measure how fast molecules move on the surface of organic glasses. My colleague Lian Yu at the University of Wisconsin has done a lot of these measurements. And for a lot of the systems that he's studied, at TG, surface diffusion is 6 to 8 orders of magnitude faster than bulk diffusion. Okay? So if you haven't thought about this before, it's sort of a funny way to make a glass. We're not making, when you cool a liquid, you make the glass, the whole glass, all at once. Okay? We're making the glass a little bit at a time from one side. We're raining molecules down on a surface. Each set of molecules has a chance to equilibrate. Eventually, they get buried by other molecules. Once they're no longer near the interface, they are really stuck. Okay? And we just keep going until we've made as much of the material as we want to make. So just one more thing. So the Tetris, you guys are probably too young to play Tetris. Okay, so the Tetris analogy on the right it just illustrates the effective deposition rate. Right? When I play Tetris, I do really well at the beginning, where things are coming down really slowly. I manage to make a really well-packed material. At the end, it's hopeless, okay, and I make a crappy glass. Okay, it works the same way in Tetris and in vapor deposition. So you have a question?
Is the deposition process continuous? Or
yes, it is. Even though sometimes it's convenient to think about each group of molecules and what they get to do, it is a continuous process.
Is there a reason for that? Could you just stop for a little bit and let it equilibrate and deposit more?
Sure, you could. It's easier just to let it happen all at once.
And the temperature is constant throughout the whole process?
That would be the standard deposition, although we have made interesting samples by deliberately changing the temperature along the way to explore the properties of the glasses. Yes. Okay, great. So this is the qualitative idea. Yes?
So I guess the speed, the diffusion, the velocity, ability to diffuse versus the dissolution rate is what makes the difference between left and right.
Right. So yes, so there's sort of 2 time scales in the experiment, at least. One is how fast molecules can explore different packing arrangements at the surface, and the other is how fast the molecules are coming down. So in a typical experiment, we're depositing a monolayer of molecules about every 5 or 10 seconds. And so we think that the mobility extends maybe 2 or 3 layers into the material. So you can think each molecule has 5 to 15 seconds in order to sample different ways of packing with its neighbors. And if this works perfectly, they will have sampled enough to be at equilibrium at 0.85 TG at the end of that process, and then they'll get buried, and then we'll make an entire sample like that. If it works perfectly. It doesn't quite work perfectly. Okay. Yes?
So the Tetris picture, is it just a picture, or can you really see that the density is higher? Because if there were particles, you would see that it would go to higher density, but in the case of molecules, I don't know what they're trying to.
Well, okay, so I wouldn't take the picture too seriously, but I will tell you about the density of the materials. So maybe that will answer your question. Yes?
How do you distinguish the defective crystal and the well-edged glass?
Okay. Okay, I'll just give you a quick answer now, and later on. So if I were making a crystal, I would expect sharp diffraction patterns when I do X-ray, and I don't see them. The other thing is that when I heat these, if I were making crystals, when I heated them up, I would expect crystals to grow and take over the sample, and they don't. When I heat these things up, they're very kinetically stable, but when they finally fall apart, they fall apart into a liquid. So I think there's 2 good arguments that these are not crystalline materials.
But when you deposit too much, then there are a bunch of defects. Or are you
Defects? Well, okay, fine. I mean, the whole glass is a defect from one perspective.
Okay.
Yeah, I think there's pretty good arguments that the materials are not crystalline. I'll show you some X-ray data later on. Okay, so maybe. All right, let's keep moving then. All right, so you got the qualitative idea. Now let me show you some real data. So there's a molecule, indomethacin. We vapor deposited indomethacin onto a piece of silicon. So the substrate is a piece of silicon. The silicon is held at 85% of the conventional TG. Okay? That is the TG that you would measure by cooling at 10 degrees a minute. We deposited until we had a film that was 600 nanometers thick. So that's about 600 molecules thick. Okay? We take the film off and we take it to an instrument called a spectroscopic ellipsometer, which does a very sensitive measurement of the thickness of the film. All right? And this is room temperature. So I take the film, I put it on the ellipsometer, I measure a thickness, okay, and then everything else here is going to be reported relative to the thickness that I started with. Okay? So the experiment goes, I heat up the vapor deposited glass, I get to here, the thickness over a pretty small length of time jumps by 2 or 3%. Okay? I get up there, I now have a supercooled liquid. Okay? So it transformed from the glass into a liquid. If I take that liquid and I cool it at 100 Kelvin per minute, I go down this orange line. If I cool it at 10 Kelvin per minute, I go down this line. If I cool it at 1 Kelvin per minute, I go down this line. If I immediately reheat, I get that hysteresis. Someone asked about the hysteresis that you see when you scan up and down through the glass transition. And so there it is. It's shown in the green curves. Okay, so everything that's up here should look familiar to you, right? You cool faster, you stay in equilibrium longer, you get a thinner film, a more dense film. So hopefully everybody's okay with that. Yeah? Okay. So it's interesting that the vapor deposited film starts down here. So it's thinner by about 1.5%. Okay? More dense. All right? That's one interesting thing. The other interesting thing is that when you heat it up, let's compare to this. This is heating at 1 Kelvin per minute for a liquid cooled glass. This is heating at 1 Kelvin per minute for a vapor deposited glass. You see, this material is starting to turn into a liquid here. This material doesn't turn into a liquid until I go up another 20 Kelvin or so. Okay? So that's an indication of kinetic stability. Okay? And this is a measure of density. Okay?
If you produce the glasses, vapor cooled glasses at a faster rate, this demand would be above that.
Yeah, so it depends. Let me just make a general statement, which is that there's a regime in which it depends. You deposit slower, you get denser glasses. And then there's a regime in which you continue to deposit even slower than that, and it doesn't change. Okay? Yeah, good. Eagle eyes. In order to, the kink is actually a failure in the ellipsometric model. Okay? And so we're modeling this as a single homogeneous material. Okay? That's an excellent description here. It's an excellent description up here. For reasons that I'll show you later, it's a bad description in the middle. And so, but it doesn't really affect your ability to extract the important information from this. Yeah?
Do you get dynamic length scales comparable with the number of layers that
The question is, do I get dynamic length scales? And I'd say the answer is well, there is a length scale running. There's some length scales running around in this problem. But let me put that question aside. I'm going to show you some more data that maybe will address the point that you're interested in. Okay, so now we do this experiment over and over and over again. And just to make things simple, let's keep the deposition rate constant, but let's change the substrate temperature. Same molecule, indomethacin. Here's the temperature of the substrate during the deposition. Just to get you oriented, this is where the conventional TG is, right here. Okay. This scale, all of these samples were measured at room temperature. Okay. So this scale tells you how much more dense the vapor deposited glass is than the reference glass, which was the liquid cooled at 1 Kelvin per minute. Okay? So all of these substrate temperatures are giving us glasses that are more dense than the liquid cooled glass. And then there's one other important thing here. This red line, I know for this molecule, I know what the density of the supercooled liquid is. And I can extrapolate that. It's just I can do a linear extrapolation and say what I expect the density to be for the supercooled liquid below the conventional TG, where it can never be measured. Okay? And that's the red line. Okay? So down to TG minus 30, right about here, my vapor deposited glasses have the density that I expect if they were the equilibrium supercooled liquid. Okay? So I'm going to interpret this plot as follows. I'm going to say what we have going on here is a competition between thermodynamics and kinetics. Okay? On this side, the kinetics are fast enough, the mobility is fast enough that our materials reach the equilibrium density. Okay? So this is going to be a region of thermodynamic control. Eventually, as I go down to temperature, I'm slowing down mobility at the surface. Eventually, I have to leave that regime. I have to go into a regime where what can happen is limited by how much mobility I have at the surface. So this is going to be a kinetically controlled regime. Okay. So let's just say this is a tentative viewpoint at this point, and I'll show you more evidence that would support this. Yes?
So in the previous graph, you mark the line where you have the vapor deposited glass, but when you repeat the same experiment at the same temperature lots of times, how much difference do you see?
That much. You're asking basically how reproducible is the experiment. So I won't go into detail about how we do these experiments, but different colors are completely independent samples. Okay? So I could say this sample right here is 1.3 plus or minus 0.1% more dense than the liquid cooled glass. Does that answer your question? Okay. Yeah?
So you said you hold the substrate at, is it 0.85 TG?
Well, for that particular experiment it was, and that's here.
So it's in the region at the crossover between the thermodynamic and kinetic.
Right. So if I want to get the most impressive density, I'm always going to work here. Maybe it's more straightforward to think about what's happening in the material if I would work over in this regime. Okay.
So does this mean that you're not creating equilibrium glasses?
Okay, so if you go back and play the tape, you will see I have not claimed to create an equilibrium material. Let me just emphasize this point. All I'm saying is that these densities are consistent with the density expected for the equilibrium material. Okay? I mean, I'm not upset with you. Sorry if I was too strong an answer.
Do you not like this question?
No, I like that question. It's a good clarifying question. Right, because when I first show you the results, I want it to look as impressive as possible, right? Okay, good. We're on the same page. All right, so now I'm going to show you an analogous experiment. So this experiment is done in my lab. This experiment is not done in my lab. It's done by Ramos, Oguni, Ishii, and Nakayama. It's not ellipsometry, it's calorimetry. Adiabatic calorimetry, incredibly precise calorimetry. Different molecule. Ethylbenzene. Actually, I'm going to draw the structure of ethylbenzene because it plays a prominent role in the talk today. And the other molecule I'm going to draw, I'm going to remind you the structure of toluene. It's the other molecule that's prominent. Okay, so Ramos et al. Vapor deposited in their adiabatic calorimeter, because they need a lot of material, so their depositions took 4 days. Okay, and they did the deposition at a bunch of different substrate temperatures, okay, and then they measured the enthalpy of the materials. So there's a lot plotted here, but let me just make clear what goes on. This is my favorite point, the green point. So they deposit at 0.92 TG. They take that sample, they cool it down to low temperature, and now very carefully as they increase the temperature, they measure the heat capacity all the way up into the supercooled liquid. And then they integrate CP in order to get H. Okay? So that's where the green curve comes from. This point is what happens at 0.93 TG. Okay? And so its enthalpy in the glassy state is slightly higher than what happens if you deposit it at 0.92 TG. Now, if you think, back to lecture number 2, you'll see that I drew curves that look just like this, right? As you age a glass, you go down in enthalpy. Then when you reheat it, the transition to the liquid state is delayed. Okay? So this is exactly the expected behavior. So now this dotted line is really important. Way up there someplace is the supercooled liquid. If I extrapolate the behavior of the supercooled liquid, that's the dotted line. Now, just pay attention to the points. These are the enthalpies of the as-deposited glasses, okay, plotted at the temperature where they were made. Okay? And so what this says is that if you deposit at any temperature at 0.92 TG or above, the material that you make, just as deposited, has the enthalpy expected for the equilibrium supercooled liquid. Okay? So this is exactly analogous to the story I just told you about the density. So I would say this is a thermodynamic control regime. This is a kinetically controlled regime. It's just different molecule, different type of measurement. Of course, one of the advantages of the enthalpy is that we know how to convert between enthalpy and potential energy. And so we know that we're way down on the potential energy landscape, because now for this sample, and for many others, we know the enthalpy. Yes?
Is that fraction where we stay on the equilibrium line dependent on the vapor deposition rate, or is that?
It certainly depends on the vapor deposition rate. So they fortuitously, I can't remember exactly what their rate was. It was either equal to ours. I think it was maybe 10 times higher than ours, because they needed a lot more material. Okay. So yes, the expectation, okay, this would be a great experiment. I would love for them to do this. I'd like them to now spend 40 days depositing instead of 4 days, deposit 10 times slower, repeat all the experiments, okay, and then I expect to see one more point on the line before we move off. Okay? But the experiment hasn't been done, so that's just my expectation. But we have done that type of experiment for other properties, and that's what we observe. Okay.
But you said that there is a limiting deposition rate beyond which things do not change.
Right, and so that would be why even if I cut the deposition rate by a factor of 10, I expect this point to remain the same. Because this is in my thermodynamic control regime. The sample already had enough time to get to equilibrium. That was air quotes, okay? And so I expect that depositing 10 times slower doesn't change that. And this experiment hasn't been done for exactly this material, but for other materials and other properties, that is the behavior that we see. That there is a line, there's a line up here someplace which is independent of the deposition rate, and then where you peel off of that line depends on the deposition rate. Yes? Mm-hmm.
These temperatures are the temperature of the substrate?
Yes, the temperature of the substrate during the deposition. Excellent point. Yeah, there's a lot of temperatures running around here. It's important to keep track of that. Yes?
Where would TK be on that plot?
Oh, excellent point. TK is, for ethyl benzene, is about 0.89 TG. So you can see I'm getting excited because we're getting close. All right? In fact, that was a great segue. So now let's try to do the configurational, let's try and do the configurational entropy. And remember I told you I didn't know how to do this completely rigorously. So we're going to go through a chain of logic here, and there's one step, big, bold assumption, okay? All right, and that's because I don't know how to do this completely rigorously. All right, so here's the idea. First of all, just remember this plot. This is configurational entropy. This is Yamamuro's work. Those 8 different liquids there. This is the supercooled liquid. This is non-equilibrium behavior in the glass. And so just because we happen to have data, I should make clear, I'm not using data from my lab for this. I'm using the enthalpy data I just shown you. That's the ethylbenzene data. And then Rodriguez Viejo in Barcelona has equivalent data for toluene. So that's the data that I'm using to construct this plot. But basically data like the last plot. So all I did is going from here to here. So for the time being, ignore those points. I just replotted the toluene and ethylbenzene data. I erased the glassy data, okay, because I'm not interested in non-equilibrium states. Okay, and I included the extrapolation all the way down to 0, so TK. Okay, so here, for example, for toluene, this is the liquid-cooled glass, the lowest temperature they could do with the liquid-cooled glass, and it is 1.1. That lowest temperature is 1.1 times TK. Okay, which is the point where this extrapolated line reaches 0. So in this construction, this is TK for toluene, this is TK by extrapolation of the supercooled liquid. Okay? So I'm taking that from Yamamuro, and now what I'm going to do is I'm going to put points for vapor deposited materials on that line. Okay? And I'm going to describe my chain of logic here. Okay? So I just told you that the enthalpy for vapor deposited glasses of ethylbenzene matches the extrapolated enthalpy for the supercooled liquid in the thermodynamic control regime. I showed you that data. I didn't show you the data for toluene, but the same thing works for toluene. Okay? I showed you that the volume for PVD glasses of a different system matches the extrapolated volume for the supercooled liquid in this thermodynamic control regime. Okay, so I think this is not a coincidence. I think this indicates that the extrapolated supercooled liquid, that its enthalpy, that the extrapolation is correct. That is, since the vapor deposited materials are giving the same enthalpy as the extrapolation is giving, I am going to assume that the extrapolated enthalpy is correct. Okay? That's the assumption. Okay, now we go back to being rigorous. If the extrapolated enthalpy is correct, then the extrapolated CP, which is just the derivative of that, is correct. Then the extrapolated S is correct, because it's also just calculated from CP. All right, as long as we're in this thermodynamic control regime. Okay, so if you let me do that, then I can take the vapor deposited experiments in the thermodynamic control regime, and I can put them on this plot. And those are what the asterisks are. Okay? And they're on that line. Okay, so they have to be on that line because the enthalpies were on the extrapolated supercooled liquid line. Okay. All right, so here's my conclusion. Now, just to be clear, I'm not claiming this is a rigorous argument. I'm just claiming it's a pretty plausible argument. Okay? I would say, from my view, a second-order phase transition at TK, which is what I would call what this would be if this comes down to 0 and then there's a kink in the entropy, that second-order phase transition is now 5 times more probable than it was before we did these experiments, because we've closed the gap between what was measured before and what's measured now by a factor of 5. At least for toluene, it's a factor of 5. For ethylbenzene, it's 3 or 4. And the other thing I'd claim is that if there isn't a second-order phase transition, something else happens. Somehow the entropy, somehow we don't get a kink at TK. we've narrowed the temperature window over where that can happen by a factor of 4 or 5. Okay, so it now should happen for toluene between TK and 1.03 TK. Okay, before it was between TK and 1.1 TK. Okay, so that's what I think we can say. And I emphasize, I'm not claiming that this argument is rigorous.
What's in the left figure? Is this something similar to the latest figure?
I'm sorry, I can't hear you.
Is the left figure relevant to the right figure?
The left figure I put up because I showed it to you in a previous lecture. These two curves here are reproduced as these two curves here with the open symbols. Okay, I was just trying to make clear where the data is coming from. So the data on the supercooled liquid is from Yamamuro's lab, and it's reproduced over there. The data on the PVD glasses is from Ishii's lab and from the Rodriguez-Viejo lab. I'm combining them all and putting them on one plot. Right, okay, so this is the supercooled liquid, and then when they cool, it falls out of equilibrium, okay? And they like to continue to calculate the entropy. And I'm a little dicey about whether you really want to call that an entropy or not, but it's certainly not relevant for the entropy crisis to look in a non-equilibrium state. So I cross this data off, and I don't plot it here, okay? Good.
If you go back one slide, your heating curve. So part of that curve is reversible, right?
Yes, the low temperature part.
Would there be a way to stay close to transition and just measure the release enthalpy of transition at there and add it to complete the integration from the liquid and obtain another estimate, or is that?
You mean I deposited here, just wait?
No, then so you can reheat it and
Yeah.
rate.
Yeah, that's what's done. Yeah, I mean, okay, I can try one more time. They deposit here, they cool to here. The experiment starts at low temperature. They measure CP as they go up all the way into the supercooled liquid. They integrate CP to get the enthalpy curve over the whole thing. Okay, so that's what we can say about the configurational entropy. Okay, I want to get to this question about huge kinetic stability, and can we say anything about tau alpha? So in fact, the kinetic stability is huge, and let me show you that in the following demonstration. This is, I showed you curves like this yesterday. This is what happens in a differential scanning calorimetry experiment. You cool a glass, and then you age it for different periods of time before you reheat it. And the longer you age, the more the curve shifts to the right. Okay, that's increasing kinetic stability. The bigger the peak gets, that's the dropping enthalpy of the sample. Okay? So on the right-hand side, I show you curves for a different molecule, but that illustrate the same kind of, the same experiment. This is the behavior of the liquid-cooled glass. This is the behavior of the vapor-deposited glass. Okay? So these are different molecules, but this is still a fair comparison. Here we increased our aging time by about 2 orders of magnitude. We moved up our onset temperature by 3 or 4 degrees. Okay? Here we moved up our onset temperature by about 35 degrees. Okay? And if you want to try and make a comparison, so I didn't say these are experiments where you age for up to 1 day. Now, if I just take that and I adjust the scales and put it on top of the vapor deposit experiment, you see, okay, well, this is the first 2 decades of aging. Okay? It's slowing down logarithmically. Okay? So there are a lot of decades, a lot of curves in between that one and that one. Okay? And so we've tried to estimate how many decades of aging in many different ways, and maybe it's 10 to the 8th. It's hard to do a good extrapolation there. Okay? So What's true is that these vapor deposited glasses show extremely high kinetic stability, much higher than liquid-cooled glasses. All right, so there's a lot of interest in this question as to whether the alpha relaxation time actually diverges as you go towards TK. So in spite of the fact that tau alpha is really too large, I'm going to make a shot at trying to estimate what tau alpha is for our most stable materials. And there's going to be a lot of assumptions here because it's really hard to say, given that I'm not willing to do an experiment that lasts more than 10 to the 6 seconds, it's really hard to say something about what's happening on the time scale of 10 to the 15 seconds. Okay. All right, but anyway, this is basically what we've tried. I'm going to go back to indomethacin. I'm going to set the stage here, log tau alpha versus inverse temperature. This is the equilibrium supercooled liquid line. Okay, that's tau alpha. This is the extrapolation of that behavior. That was obtained by fitting this segment to that VFT equation with a divergence in it and just extending to lower temperatures. So this is this line. And this is the behavior expected for tau alpha for a glass that's liquid cooled and not aged, just cooled at 10 degrees a minute. Okay, so this is the context. And now where do our vapor deposited materials lie? Okay, so we deposit down here because this is where we make the most stable material. So we've waited around for parts of a day, nothing happens. So I can't tell you really anything about how big the barriers are at this temperature. So you do what experimentalists would do. They say, well, let's heat the sample up and make it fall apart. Okay, so we take a sample, we try and make the same glass over and over again, and then we heat it up to different temperatures, and we measure how long does it take that glass to fall apart into the supercooled liquid. And so those red points, those are honest measurements, okay? And they're from, 10 to the 3 to 10 to the 6 seconds. And you can see that those are pretty big times compared to the alpha relaxation time. That's because these materials are really well packed. Okay, so now what I'm interested in, though, is if I extrapolated to low temperature, what would the time be? So now I have a problem. There are different ways of doing this extrapolation. And I would just say I've shown two reasonable ones. Okay? And I don't know which one's right. Okay? And so there's two reasonable extrapolations. And then I know what the enthalpy of my glass is. And I'm going to use that enthalpy to figure out what temperature I should plot my vapor deposited sample at for this comparison. And so if you're used to the language of fictive temperatures, I'm comparing the supercooled liquid and the vapor deposited glass at the same fictive temperature. Okay? So this kind of calculation, which has some approximations in it, clearly, says that we would expect at this temperature the stability, the structural relaxation time for this material to be somewhere between 10 to the 11th and 10 to the 15th seconds. Okay, so it sort of makes sense that we didn't see much happen in 10 to the 5 seconds because it's a really long time. Those estimates on the upper end are consistent with this diverging function, and they would also be consistent with other functions. Okay, so that's what we can say. The alpha relaxation time is long, but if some experimentalist, some clever simulator can come out with an idea for how to do this extrapolation better, that would be really helpful. Okay, because we'd really like to be able to say something more precise about what our alpha relaxation times are at low temperatures. But the good news is they're big. We would estimate at least 10 to the 8th times longer than the liquid cooled glass at that same temperature. Okay? So these are quite kinetically stable materials.
So in this case, you change the temperature of the substrate or a whole sample?
All right, let me clarify. So let's see, there's 4 data points here. So 4 times we made the substrate temperature 0.85 TG. We made samples that we thought were identical 4 times. That was at 0.85 TG. This is above TG. Now we jump the temperature up to some temperature above TG and we hold it. And we have some measurement that tells us when the structure changes. Okay? And we just see, so when you do that, for a long time nothing happens, and then eventually you see changes in the structure or in the dynamics or in something in the material that tells you you've recovered the supercooled liquid. And that can take anywhere for these measurements between 1,000 seconds and 1,000,000 seconds. And those are these points here. Does that answer your question? Okay, good. Okay, so now this next story is a bit of a little sidelight, but it's such an interesting one that I can't resist. So these materials have extremely high kinetic stability. And in spite of the fact that they're amorphous, and we can discuss the evidence for that more later, if you have a thin film of these materials, they melt like a crystal. Okay? That is, they start to become a supercooled liquid at the free surface, and there's a front that propagates through this material at constant velocity. Okay? So just to emphasize, this is unprecedented for amorphous materials. So what you expect when you have an amorphous material is you have a glass, you heat it up above TG, sort of all parts of the material become a liquid more or less at the same time. Okay? What I'm going to show you is that's not true. I'm going to show you that the top 100 nanometers becomes a liquid first, then the next 100 nanometers becomes a liquid, then the next 100 nanometers, and so on. Okay? And so let me show you the evidence for this, and then I'll just come back and discuss briefly, once you think about it, why this makes sense. So here we vapor deposited a film that's 1,500 nanometers thick. We put it on the ellipsometer. Now this time we use a good model for the ellipsometry, one that knows that the material might not be homogeneous. And what the model tells us is that there's an interface inside the sample with a discontinuity in the index of refraction. And there's some light reflected off of that interface. And so we can do this experiment in real time. We can track the position of the interface as it moves down through the sample. And what that interface is the highly stable glass transforming into the supercooled liquid. Okay? You can repeat the experiment with a thinner sample that's prepared the same way, and you get the same slope. Right? So if this were a crystal, we'd say this is the melting velocity of the crystal, and it should be independent of the size of the crystal. Okay? So this really is behavior that's analogous to crystals. So I had never really thought about this carefully before, but of course the whole reason why crystals do this has nothing to do with periodicity, but what it has to do with is the fact that the barriers for rearrangement are much higher in the middle of the crystal than at the surface of the crystal. And so when you heat it up, and the whole material wants to become a liquid, it starts from the surface because that's where the barriers are the lowest. And then the surface is a liquid, and now there's crystal material in contact with the liquid, and that's where the barriers are the lowest. So that part melts, and so forth. So the same explanation works here, except we just don't have a periodic structure. The activation barriers inside of this material are so high that if you're 500 nanometers away from the surface, you're going to be rescued from your trapped state by a front, moving 500 nanometers from the free surface and freeing you from the configuration that you're in before anything else happens. Okay? So I think this is a really cool feature of these materials. Just to maybe, this is actually at a quite high temperature, 16 Kelvin above TG. Under these conditions, a liquid cooled glass would turn into a supercooled liquid in less than 1 second. This is taking 10 to the 4 seconds. Okay, that's just another indication of the very high barriers there are in this material. So here, I go out on a limb. I expect an ideal glass to also have this property. I think the barriers in the middle are so high compared to the surface that it's going to melt like a crystal. So now I should make something clear. In these experiments, I used really thick samples. So I didn't have to worry about the material falling apart because it was of a front from a free surface. Eventually, something will happen in the interior of the material that will limit its stability, and that's what's actually being measured here. Okay. All right, so we're making good progress here. We didn't see any evidence of aging. We have a really low enthalpy. We have huge kinetic stability. We have a big tau alpha, but it's really too large to measure. We made a stab at the configurational entropy. It's pretty impressively low. So what we're left with is low temperature behavior. And now low temperature behavior is going to include what happens at a few Kelvin, so what's traditionally interpreted in terms of two-level systems, and also the beta relaxation. Okay? So we want to go through that. Yes, Ludovic.
So why do you expect the ideal glass to have the same property as the electron propagation? I mean,
Because I make a very general argument about where it comes from.
does it mean that you have an underlying phase transition?
No.
Phases?
No. It just means that barriers are really high in the interior of the material, and generically I expect them to be lower at the surface. So.
We use the language of first order phase transition.
Can you speak louder?
You use the language of first order transition, nucleation and growth. You have a surface tension between two phases. Here it's a surface tension between the liquid and the liquid. You have an underlying phase transition in your head, or you don't need it?
I don't need it. Maybe I should need it, but I don't need an underlying phase transition to explain this. I just need barriers in the interior. I'm giving a kinetic argument. Barriers in the interior are really big. They must be lower at the surface. Therefore, it's going to grow in from the surface. That's my prediction. What about the interface? Okay. I think maybe we should pick this up later. Okay. Did you have a question, Patrick?
Yeah, so I mean, the argument that you're using could apply just as well for a bulk glass, right? You also have a surface.
Yeah, it would apply if there's a sufficiently big difference between the activation energies, and I guess there isn't.
But would it be worth going back to those samples and trying to figure out whether there's a regime where it would melt from the surface instead of?
It would definitely be worth it, and we have tried and haven't found it yet.
Okay,
But that doesn't. I think it will work if you do the right experiment. Okay. Yes. I think if you age a liquid-cooled glass and you do an extremely sensitive experiment, you're going to see a front that moves from the free surface. It might only propagate 10 nanometers before something else happens. But I think you're going to see it. Yeah. Okay, so I want to talk about the beta relaxation process. Just so everybody, and I'm going to use toluene, which is the same example I used in lecture 2. Remember the beta process, according to NMR experiments that have been done in toluene, is sort of a millisecond process, and one part of it is that the molecular axis explores a narrow range of different orientations, and the experiments fit to a distribution that looked like this. Okay, so our question was, what happens if we measure the beta relaxation in one of these glasses that are low on the energy landscape and have high kinetic barriers? And so this is the experiment. We vapor deposit. Now, we're going to do a dielectric relaxation experiment. So we vapor deposit onto a substrate that already has electrodes patterned in it. So we can directly do dielectric relaxation here. That's what the substrate looks like. And so let me walk you through the results here. Now, up to this point, I've always shown you the dielectric loss as a function of frequency. So there's a twist here. Now I'm going to show you the dielectric loss at fixed frequency, 1,000 hertz, as I change the temperature. Okay. And so this is a really stable glass. This is the dielectric loss as we heat it up. Across this regime, this is reversible. So this is deep enough in the glass, you can scan up, you can scan down, you'll always measure this loss. Once you get to this temperature and you get to the open points, the sample is starting to transform into the liquid. By the time you get to the end of the open points, it's completely a liquid. And then this is now the supercooled liquid, okay? So that's what happens in run 1. Now you take the supercooled liquid, you cool it down. Now we have a liquid-cooled glass, and you repeat the experiment, and you get the blue line. And then you do it again, and you get the green line, okay? And so this is the alpha process. And the fact that the stable glass joins the alpha process late is consistent with its kinetic stability, okay? But for our purposes, this is the interesting thing. This peak is the beta process in toluene. And this is a log scale. It's suppressed by a factor of 3.4 in a sufficiently packed glass. And if you want to see the data on a linear scale, you can look up there. Okay, so I can only offer you a possible molecular interpretation. I know that in this distribution, the average change in orientation was 7 degrees. If I make the average 3 degrees instead of 7, then that would match this data. Okay? Of course, I could also just eliminate these, and that would probably match the data too. Okay? So I can't tell you in detail what's happening other than somehow, as you have a better packed glass, a denser glass with higher barriers, this beta process is exploring a tighter and tighter group of states. And I would imagine something similar is going on with translational degrees of freedom, but I don't have that data. Okay, so to put this in context, we said, well, let's try to age a liquid-cooled glass. So we made a liquid-cooled glass. We went a few degrees below TG to 110 Kelvin, and we repeated this dielectric experiment over and over again. We waited up to 200 hours, a little more than a week. We did see that we started to suppress the beta process as we moved down the landscape. And then, if you want to, this is what we measured as we aged the ordinary glass. This is what we measured in the vapor deposited glass. And so this estimate would say you'd have to age for about 3,000 years in order to achieve that same stability. So I have to confess, I never considered this question, but my collaborator Ranko did. And I really like that question. The question is whether the strength of the beta relaxation is an indication of our approach to the ideal glass state. And I think you can make a good argument that it is. And let me make that argument now. Okay, so this is the relaxation map for our experiment. This is the alpha process. This is the beta process for the liquid-cooled glass. This is the beta process for the vapor deposited glass. But the most important plot is right here. It's the inset. This is the amplitude of the beta process in the equilibrium supercooled liquid as you go down in temperature. And if you take that and you just do a linear extrapolation, it hits 0 at about 109 Kelvin, and the Kaufman temperature is 108 Kelvin. Okay? So if I just use equilibrium data, I extrapolate, it looks like the beta process would go away when I made the ideal glass. And that star is our sample. Okay? And it looks like it's on that extrapolation. Okay? So this would suggest, so just to be clear, I'm not claiming we made the ideal glass. I'm claiming that we've moved 3/4 of the way there, and that it's fair to make a little bit of an extrapolation at this point. And so if I make that extrapolation, this suggests, at least for toluene, that the ideal glass will not have a beta relaxation. That these secondary relaxation processes, that the amplitude will just be completely, the molecule's orientation will be essentially completely locked in place by the very tight packing. Maybe I'm wrong, but That's what the data suggests. Okay, so very low temperature behaviors of glasses. So we talked briefly about this in lecture 2. The heat capacity of glasses below a few Kelvin is different than that of crystals. It's higher. This is work. This is a collaborative work. Didn't involve my group. It was Miguel Ramos and Javier Rodriguez Viejo. So they took one of my favorite molecules, indomethacin. They vapor deposited it, and they did low temperature calorimetry at just a few Kelvin. And so here's their data. And let me just point to some of the features. First of all, this is a temperature scale, logarithmic, 10 Kelvin, 1 Kelvin. This is heat capacity divided by T cubed. Okay, so here's your reference. This is the crystal. You see the crystal has a low heat capacity, and down to the lowest temperature they can measure, it's consistent with T cubed, with the Debye model. These conventional glass, this is the liquid-cooled glass. You see when you plot Cp versus T cubed, it's shooting up. Okay, that's because it's basically going linear. Okay, and so this is what's happening in a liquid-cooled glass. These two are two different samples of vapor-deposited stable glasses. At 0.85 Tg, the same temperature I've been telling you about for indomethacin. And in this regime, below 3 Kelvin, they're consistent with a T-cube scaling. Okay? Now, this is a fun fact. You might say, well, darn it, why didn't they keep going? Wouldn't it have been nice to know what was going to happen down here? So the issue is that, of course, there's a calorimeter involved here, and it has its own heat capacity. And when your sample heat capacity gets too low, you just can't measure it anymore. And so that's why the lower the heat capacity is, you stop at a higher temperature in these measurements. So they did the entire range that their calorimeter could reach. Okay, so if you would insist on interpreting this data in the conventional method using two-level systems, then you would have to conclude that the density of two-level systems was either substantially lower in the vapor-deposited glass, or that the energy scale was shifted such that this uptick is going to happen at a lower temperature than's been measured yet. Okay? So I think those are two scenarios that are consistent with the experimental data. And then there may be other interpretations that don't involve two-level systems that are also consistent with the data. I guess the point that I would make is that for a long time it was thought that these two-level systems were universal features of amorphous materials. And I think these vapor-deposited glasses are amorphous materials, and they have quite different levels of these things. And so I think this is a real opportunity to learn about what these things really are, because now we have a knob that we can turn in the lab and move the heat capacity behavior around. So I'm never going to do 1 Kelvin experiments, but I hope some other groups are going to jump in and do more here. There's one more experiment that's been done in this regime, and it's on vapor-deposited silicon, so pure silicon. This is work by Francis Hellman's lab. And so I'm not showing you the raw data. I'm just showing you the interpretation of the data in terms of two-level systems. And so this is the temperature they vapor deposit at versus the estimated TG for this material. This material crystallizes when you heat it up, and so there's a window where you really can't access it. But the important point is that there's almost a factor of 100 difference in the density of the two-level systems based on the measured heat capacities. So this is, and what's the other point? And the other important point is that as you go towards 0.85 Tg, the density is getting lower and lower and lower. Now, at this point, we don't know the kinetic stabilities of these samples. And so there's a lot of additional experiments that you would need to know whether this really fits into the same pattern. But I think it's, at a minimum, here are two important examples of how non-universal the low temperature properties are of amorphous systems. Yes?
So the two level systems might be missing. How about the universal internal friction and the universal dielectric loss in these PVD processes?
So there's some information about that in Hellman's paper. So I would refer you to this paper. I don't remember it. Okay. Okay, so that's the really low temperature behavior. All right, this is working perfectly. So one last topic. Hey, actually, it didn't make the list. Somebody might have asked, what's the structure of the ideal glass, right? And so we have tried to do some measurements to characterize the structure of PVD glasses. And let me just introduce you to the idea about how I think about this, because I'm not going to, I don't have the time to drag you through all the details, and you don't have the energy to listen. So this is how I think about what happens in a liquid-cooled glass. And it's only an approximation, but I think it's a reasonable one. As I cool the liquid, okay, I must be changing the structure of the liquid because the dynamics are indicating that the effective barrier is growing. Okay, so there are changes in the structure of the liquid. Even if I'm not very good at doing an experiment that quantify what those changes are, I believe that they're there. And then when I go into the glass, to a first approximation, whatever structure the liquid had right here is what gets trapped into the glass. Okay? Now, it's only an approximation, because as I go through this regime, the material actually can age quite rapidly at the beginning. Okay? But it's a first good idea. And if I stay in equilibrium longer, then the structure that was tapped in this glass looks more like the equilibrium liquid at a slightly lower temperatures. Okay? So that would be my qualitative answer to the question of, in a liquid-cooled glass, where does the structure come from? Okay, well, we can't use that same answer for vapor-deposited glasses because they never see the liquid. They never see the equilibrium supercooled liquid. So my answer is the only place there's mobility in this glass is right here at this interface. And so whatever structure is in these materials is trapped in it based on what's accessible during the experiment and what's happening right at the interface. So now let me try and be more quantitative about this, but I just wanted to give you the idea first. Okay, so an important fact. Interfaces are anisotropic. And most of the glasses that we've studied, when we measure their structure, they are also anisotropic. And I think that anisotropy in the bulk material is a result of the fact that we're preparing these materials in an anisotropic way. Okay? And let me just show you two examples of that. Okay? So this is indomethacin. All right? This is a very simple measure of anisotropy. You get it from those ellipsometry experiments. It's the birefringence. It's the difference in the index of refraction for light, if this is the film, for light that's polarized like this and light that's polarized like this. Okay? So there's a temperature range when we vapor deposit down below TG, where we're making, by this measure, isotropic materials. And then below that, we make anisotropic materials. Okay? Yes?
Where is the thermodynamic control regime?
Excellent point. It goes to about right there. Okay, so we've done more direct measurements or more local measurements of structure. So here's a molecule I haven't introduced yet. Its acronym is TPD. It's used in OLEDs, organic light-emitting diodes. It's a hole transport material. It's an organic semiconductor. And so actually most of my group right now is studying materials like this. because they have potential applications if you can make different kinds of glasses that have different semiconducting properties. But let's not worry about that. Let's just say it's another molecule we can vapor deposit. This molecule, one of the things that's nice about it is TG is well above room temperature, so we can make glasses with it, and we can ship them off to a synchrotron, and we can do two-dimensional X-ray characterization. So maybe the details about how we do the experiment aren't so important, but it's a two-dimensional X-ray experiment, and so I can tell you that this is scattering in the plane of the sample, and this is scattering out of the plane of the sample. Okay? So the other thing I can tell you is that if you do this for an isotropic sample, then any cut you take along here looks identical. All right? And so this sample is clearly quite anisotropic because scattering is bunched up into the out-of-plane region. And in fact, from this distance here, I can tell there's a tendency for the molecules to line up like this in that film. This film shows the opposite behavior. And because that peak is brighter in plane, I can tell there's some small tendency for the molecules to do this more than they would at random. Okay? Because otherwise I would see an isotropic scattering pattern. So we've studied this for a lot of materials. And you know, there are a variety of different patterns, but this is just two representative examples. I should also tell you that this is a highly kinetically stable glass. This is a highly kinetically stable glass. And in between, there's a highly kinetically stable glass, whose scattering pattern, you would look at it and you'd say it's isotropic. Okay? So all that happens. Yes?
Should we connect these two-dimensional patterns with birefringence going up and down?
You should, but not this particular data.
Yes.
In fact, there is a perfect correlation with the birefringence in that, which is completely consistent with this story that I just told about how the molecules are oriented. So we can also get that information from the birefringence. Okay, so I think I just have time to do this. So one thing that people will be asking is what about ethylbenzene and toluene? Since I relied on those to get to do the Kauzmann extrapolation, and the answer is I don't have any information about the anisotropy in those glasses because they're inconveniently low temperature. They're TG. They don't allow. I can't make those glasses and take them to the synchrotron. Okay. But based on what I've seen for other systems, my expectation is that if you look hard enough and you're a little bit, considerably below TG, you will find anisotropy in every vapor deposited glass. Okay, just what my expectation is. Okay, so I think this is the thing that I'll end with. So this anisotropy in the context of organic electronics is actually useful. And in particular, there's evidence that this kind of packing, you get higher charge mobility because you're stacking up the pi systems in a favorable way. And so we have spent a lot of time trying to understand why you get these different patterns when you vapor deposit. And I think this is the thing that I'll end on. So back to the qualitative picture, it all comes down to what the molecules want to do right here. Okay? So with our collaborators Juan de Pablo, we have done a bunch of computer simulations to try to understand this process. And I'm not going to show you simulations. I'm just going to show you the cartoon picture that summarizes what we learned. And then this will be it. So one of the systems that Juan simulated was a film on a substrate of TPD, exactly that molecule I was just showing you. And So these simulations are done at high temperatures. They're straight molecular dynamics. And what you see, if you look at these are liquids. So if you're away from any interface, these are isotropic materials, okay? But liquids don't have to be isotropic at interfaces. And they're anisotropic both down here at the substrate, which I don't care about, and up here at the free surface, which I do care about. Okay? And what this plot illustrates is that right at the free surface, there's a tendency for molecules to be lying flat. Just below that, there's a tendency for molecules to be standing up. And in fact, it probably would have been better if these standing up ones were poking through and also touching to the same distance. That would be a more realistic representation of what's in the substrate. Okay, so any of you can do this. You can go run your own simulation of a equilibrium thin film of anisotropic objects. And I think if you choose objects that are this shape, this is what you're going to see, because we've tested it with some more coarse-grained models, and this is what we commonly observe. Okay, but to the point, how does this tell me about the structure of vapor-deposited glasses? So I like this explanation a lot, even though it wasn't my idea. It was Juan's idea, and it came from the simulations. When you deposit at a low substrate temperature, there's not a lot of mobility. And of course, there's always going to be more mobility right at the free surface than anywhere else. So let's imagine that low substrate temperature means that at the deposition rate you've chosen, you only have enough time to equilibrate this very top layer. Okay? So then you're going to put that layer down, and then you're going to deposit more molecules. And now they're at the free surface, and they want to lie down. The ones just below them don't want to lie down. They want to stand up, but there's not enough mobility for them to do that. And so you build up a non-equilibrium film that looks like that. Okay? On the other hand, if you deposit at a higher temperature, such that this much material at the interface can stay in equilibrium during the deposition, then this is going to be the structure of the interface during deposition. Okay? And so I'll have this, and then I deposit one more layer. And so that new layer looks just like this. And now there's a layer that's standing up that at equilibrium would not like to stand up. But that's too bad. It's stuck. There's not enough mobility. And so that's how we end up trapped into this state. So that was the last thing I wanted to say, is just give you some idea of where the anisotropy comes from in these materials. So thanks for your attention. If you have any more questions, I'll try and answer them.